Okay, so our next talk will be presented by VR Sathiyanarayana. It's on verifying almost sure termination for randomized distributed algorithms.
Thank you. Hey everyone, I'm Satya. I'm here to talk about our work on verifying almost sure termination for randomized distributed algorithms. This is joint work with Constantin, Rupak, and Harshit. So, our work studies the termination of randomized distributed algorithms. What are these things? Well, in general, distributed algorithms specify instructions to be followed by a number of independently executing processes. These instructions can have the processes change state locally, perhaps in a randomized way. It can also have the processes communicate via an unknown network. This network can ascribe arbitrary delays to the messages, and it is the job of the algorithm to be able to deal with such arbitrary delays. Now, in addition to having to deal with delays, the algorithms must deal with something called process faults. There are two kinds of process faults. The first are the crash faults, where a process just stops executing at some point, meaning it can no longer receive messages or send messages or do anything else. The second kind is a bit more fun. These are the Byzantine faults, where, like the Byzantine generals problem, we have traitorous processes that can send arbitrary messages with just the goal of disrupting algorithm execution. Right? So these are distributed algorithms. There are a number of reasons for having them. We have algorithms for leadership election. We have algorithms for maintaining shared ledgers. But in our work, we study the consensus algorithms for something a bit more fundamental called consensus. So in the case of consensus, we have a number of processes that each start with a binary value. And at the end of the algorithm, they all form consensus on the binary value. So consensus is a fundamental property of distributed systems. It is essential to showcase the reliability of the system in the presence of process faults. It's important to note that randomization is essential to achieve consensus. Right? These lovely folks over here have shown that there is no deterministic distributed algorithm that achieves consensus. And in the current world right now, there are a lot of algorithms for consensus. But unfortunately, the proofs that some of these algorithms come with are a bit intuitive and make some implicit assumptions. For example, Benor's algorithm was proved against a much weaker class of network behaviors and was proven correct for stronger behaviors much later. And there have even been published algorithms with liveness flaws, meaning that you could sequence message deliveries in these algorithms to ensure that they never terminate. Right? So because of all of these things, we wanted to look for machine-checked proofs that these consensus algorithms indeed terminate. And our way of tackling this problem is to use proof rules for termination. Proof rules in general are just ways to encode certificates of termination in a machine-checkable way. The most classic example of a proof rule for termination is the ranking functions. These guys just encode the length of the terminating run of a program, and this length must reduce at each step, right? And in our setting of non-deterministic probabilistic programs, there are already a number of existing proof rules for termination. And there are even some verification infrastructures where we could just implement one of the consensus algorithms and give it the proof rules, and we can get an yay. This algorithm does actually terminate. Right? So how do we use these things exactly? Well, we use the non-determinism that these programming languages provide to serialize the execution of a distributed algorithm. At each point, we will take the global view of the distributed algorithm, non-deterministically pick one of the actions that are available there, and then use any of our AST hammers inside the AST toolbox to prove the termination of the system. Right? So this is a nice overarching plan, but unfortunately there is one problem. Distributed algorithms make implicit fairness assumptions. These assumptions are also transferred when we look at it as a probabilistic program. And these are quite simple assumptions, like every process must eventually execute infinitely often, and every message that is sent to the network will eventually be delivered by the network. Unfortunately, none of the existing proof rules for probabilistic termination incorporate fairness assumptions. And this exactly is where we come in. We have shown certificates for the almost sure termination of a number of consensus algorithms, including a broad general class of algorithms that use a binding crusader abstraction, using a new proof rule for almost sure termination that considers fairness. Okay? So in the rest of the talk, I will show you how we use this thing to prove the termination of the first algorithm that solves distributed consensus. Okay? This is Ben-Orr's algorithm. It is the first, and it's a quite simple and elegant solution to the problem of distributed consensus. And in this slide, I will show you what this algorithm's execution will look like for the case where you have 5 correct processes, and 1 Byzantine process. Okay? I will show you asynchronous execution because it is just simpler to show in a slide. So, Ben-Orr's algorithm proceeds through several rounds. Each round has 2 stages. Whenever a process enters a round, it enters with a Boolean value that it would like to propose. These are the ticks and the crosses next to the processes. Right? And in the first stage, the process just broadcasts the value that it wants to propose to every other process in the network. Okay? And after broadcasting, it waits for 5 responses from the network. This 5 corresponds to the number of non-faulty processes in the network. And once it has all of these 5 messages, it analyzes them. It sets a local value it checks if it has received 4 messages of the same type. If so, it sets a local variable to the value of those 4 messages. Otherwise, it sets them to question mark. This number 4 just corresponds to a way of determining majority in the presence of Byzantine faults. Okay? Now, after setting this internal variable, it just transmits this internal variable again to every other process. Note the action of the Byzantine process here. It can send whatever message it wants. And it indeed did send whatever message it wanted in the previous round, in the previous stage. Right? So, in the second stage, we broadcast this internal variable, and then you again wait for 5 messages. And after waiting, you get to analyze these messages and decide if you get to terminate or decide what you want to do in the next round. Okay? So, a process gets to terminate if it has received at least 4 messages of the same type. None of the processes here have managed this. So, what the processes can do is, if it has received at least 2 messages of the same type, it can propose the value of that message in the next round. This is what is happening to the processes on the left. And this value, too, is again just 1 more than the number of Byzantine processes that are in the network at the moment. Okay? And if processes don't even get this, the only thing they can do is toss a coin and propose the output of this tossed coin in the next round. Now, while I have presented a synchronized view of Ben-Orr's algorithm, it is important to remember that Ben-Orr's algorithm isn't really synchronous. It's for asynchronous consensus. Processes can be in different rounds at every possible state. Okay? Now, why is this algorithm correct? Well, it's correct for two pretty simple reasons. The first is that if all non-faulty processes begin a round of Ben-Or with the same value, as is happening here, then the algorithm terminates in one round. This is not too difficult to show. And the more interesting thing is let's say the purpose of the coins, purpose of all the coin tossing. You can show that there exists a lucky sequence of coin tosses spanning 2 rounds, after which all non-faulty processes begin the next round with the same value. Meaning that if things go perfectly well, the algorithm will terminate in 3 rounds. This fact is exactly what we show, what we encode as certificates in our proof rules to verify the termination of this algorithm. Okay? Well, this is as good a point as any to segue into proof rules. Well, we talked about ranking functions earlier, but we want to actually analyze proving termination of probabilistic programs like this one. Ranking functions are not enough because here you decrement x or do nothing with equal probability, right? But you have to reduce with probability 1 every time in a ranking function. So, to prove termination, generally speaking, we have shown last year that you need 2 kinds of certificates. The first certificates are called the probabilistic variants. They were introduced by McIver and Morgan in 2005. The second is a super martingale. This was studied a couple of times in the literature before. So the variants are a generalization of the idea of encoding the length of the terminating run. These ask for functions that reduce with a minimum probability at each execution step. So for this particular program over here, the simple function u of x is x is a variant. However, for variants to work, these functions have to be bounded, which can work for this program as long as you have a fixed initial state, right? However, for other programs, variants don't work. They're not enough. For example, in this program, a simple one-dimensional random walker, there exists no bounded variant that can work. And for this reason, we need super martingales. Super martingales essentially support the variants. They are simple functions that do not increase at each execution step. For the simple one-dimensional random walker over here, a simple super martingale that simply assigns, let's say, outputs the value of x at each state is a super martingale because it does not increase in expectation at each step, right? And how do the super martingales support the variance? Well, you just require the variance to be bounded within sub-level sets of the super martingale. In a sense, you just require the variance to be bounded while the super martingale itself is bounded. Okay? So this is the proof rule that we proposed last year. Can we just use this proof rule directly to prove the termination of consensus algorithms? Well, again, not quite, because consensus algorithms like Ben-Or assume fairness constraints, assume fairness. And the place where fairness affects the proof rule is in the variance. You see, the variance require a reduction with a minimum probability at each step, no matter how the non-determinism is resolved. This is because the variants assume the worst case resolution of non-determinism, which in the case of consensus algorithms can be unfair. For example, processes can be ignored forever, or Byzantine processes can be scheduled continuously after some point, or some messages that were sent to the network would never actually be delivered. And we have to augment or modify variants so that they actually account for fairness. Well, how do we do this? Well, let's start with something a bit simpler. Let's take this program that we've seen earlier, and let's augment it a tiny bit. Now there is a non-deterministic choice where you could either reduce x or with probability half or do nothing. You can choose to do nothing if you want to, non-deterministically. So this program will terminate if you assume fairness. Fairness here means that both directions, non-deterministically, are taken infinitely often. And the only way you will not terminate is if you keep taking skip the second direction infinitely often. So in a sense, the first direction is helpful toward termination, while the second direction is not, right? So this idea of a helpful direction toward termination was formally noted by Francis in 1986, where essentially to prove fair termination of non-deterministic, non-probabilistic programs, you find a helpful direction function that is enabled whenever that essentially tells you which direction to take to reduce the variant. And how does this work? Well, okay, right. In this particular example, the helpful direction is obviously just the first direction, right? So how do we modify variants so that they work with the helpful directions? Well, you kind of just need to reduce the variant whenever a helpful direction is taken and keep the variant the same, or at least not increase the variant otherwise. This is our new proof rule for showing almost sure termination under fairness constraints, and we will use this to prove the termination of Benor. So how do we do this? Well, remember these two theorems. To codify this, let's make a definition. Let G represent the total number of steps of Benor in a single round across all processes. Note that in the first theorem just says if all non-faulty process, first theorem just requires one round of execution to terminate. This requires G steps. The second theorem requires 2 G steps because the lucky sequence spans 2 rounds. So the variant, which is still some idea of a length of a terminating run, from the initial state will be 2G plus G. And is this enough? Well, not really, because the second theorem requires the lucky sequence of coin tosses to happen. What if the coin tosses are not so lucky? So to be able to do that, let's track that. Let's add a variable tracking the number of unlucky coin toss sequences so far. And each time a coin toss sequence is unlucky, you have to try it again. So that adds another f times 2g to the variant. And finally, just reduce the number of steps completed so far. And this gives us a probabilistic variant for Benor's algorithm. Now, in interests of time, I will not go into too much detail about the other certificates here. We can show that this particular super martingale works for the variant. And importantly, this particular choice of helpful directions will work. Essentially, choosing any non-deterministic choice that changes the local state is enough to ensure that this value R over here reduces. Okay? Now, we have in our paper validated these certificates for Benor using Caesar, the verification infrastructure that I mentioned earlier. And I'd like you to note the exponentials in the super martingale. This means that the super martingale is outside the reach of existing template-based methods to prove the almost sure termination of probabilistic programs. Okay? Now, to summarize, in our work, we have machine-checked the almost sure termination of an elegant randomized protocol for distributed consensus using a new general proof rule for deducing the almost sure termination of non-deterministic probabilistic programs under fairness constraints that can potentially be applied to other distributed algorithms to prove their termination. In the paper, we have machine-checked termination proofs for a general class of efficient consensus algorithms tolerating crash and Byzantine faults. As future work, we would like to take a look at, we plan to take a look at harder fairness assumptions and algorithms with weaker guarantees and algorithms that incorporate cryptographic reasoning. Thank you for listening. I'm happy to take questions.
Questions?
So when you were describing your fairness assumptions, you said all messages are eventually delivered. Mm-hmm. It's a pretty strong assumption, right? So you don't allow any message to be dropped? Or did you mean that you're going to have like infinite retries?
We just assume very little about the network. It could potentially happen that a message is delivered after many, many retries, yeah. But these algorithms were proven correct under these fairness assumptions, so we just took these fairness assumptions and just wrote them down, yeah.
So down here.
Oh, sorry, yeah.
So a common way of dealing with a fairness assumption is to assume like a partial synchrony model where eventually, right, the system goes into a state in which everything is fair. Mm-hmm. I've been trying to connect what you're doing to that model, which I think is a more standard way of doing this. So can you just relate that a little bit? Sure.
Partial synchrony, in a sense, kind of deals with something that is also called finitary fairness, I think, in the literature. This was introduced, I think, by Rajiv Vellore and Hensinger a couple of years back. So in partial synchrony, you just say there is some bound such that messages are always delivered under this bound. Or let's say sometime in the future there is global across all messages, you see. That's the entire point. There is some bound is the entire point. But here we just assume that there is no, let's say, upper bound on on a simple global execution of how much time it takes for a message to be delivered. So this is the difference between the two. I believe with partial synchrony, the proof rule can become a bit simpler, but I'm blanking at the moment, I'm sorry. More questions?
I have a somewhat speculative question. So in the non-probabilistic setting, fair termination, non-termination is often seen as a representative problem, and then you can do many other things once you solve this. Mm-hmm. So is there a hope to kind of have a more general class of problems that you can solve in this setting, like defining some language like LTL or something?
Yeah, I mean, yes, I think that would be something that we would like to do, but for that, I think the best way to do that, this proof rule can already solve any of these kinds of consensus protocols or any distributed protocols for which the proof rules can apply, but we have no completeness results. That's the bottleneck at the moment. If we had completeness results, we can solve a general class, any kind of general class of problems with these proof rules.
Okay, so let's thank the speaker once again.